Imagine a metal rail resting outdoors in the early morning. As time passes, sunlight warms the air and the rail. As the temperature of the metal rises, the rail becomes slightly longer. The change in length may be too small to notice without careful measurement, but the dependency is real and important. There are three quantities in this story. Time changes. Temperature changes because time has changed and the surrounding conditions have evolved. The length of the rail changes because the temperature has changed. The effect of time on length does not act as a single unexplained jump. It passes through temperature. This is the basic situation addressed by the chain rule. The chain rule is a method for following change through intermediate quantities. It allows us to begin with a change in one variable, trace how that change alters a second variable, and then determine how the alteration of the second variable affects a third. This central idea is causal, although calculus itself does not require a philosophical theory of causation. What matters mathematically is dependency. If temperature depends on time and length depends on temperature, then length depends indirectly on time. The chain rule tells us how the rate of change of length with respect to time is assembled from the two simpler rates involved. One rate describes how quickly temperature changes as time passes. Another describes how sensitively length responds to temperature. The overall rate of change of length is obtained by combining these two local sensitivities. Let us pause and reflect. Time does not need to appear directly in the law describing thermal expansion. The expansion law may speak only about temperature and length. Nevertheless, because temperature itself changes with time, the length inherits a dependence on time. The chain rule makes this inherited dependence precise. Real systems frequently contain many such intermediate quantities. A change in electrical current alters heat production. Heat production alters temperature. Temperature alters electrical resistance. The changed resistance then influences the current. In a more complicated model, pressure, density, concentration, and geometry may also intervene. The visible input and visible outcome may be separated by several hidden layers. The chain rule is calculus for following a pathway through those layers. It replaces one complicated dependency with a sequence of simpler dependencies. To understand this more carefully, it is helpful to distinguish three rules. There is an input, an intermediate quantity, and an outcome. The input is the first quantity whose change we consider. The intermediate quantity receives that change and carries its effect forward. The outcome responds to the intermediate quantity. Consider the price of a product, the number of units demanded, and the revenue earned from sales. Price is an input that a seller may adjust. Demand responds to price. Revenue then depends partly on the resulting number of units sold. In this simplified description, price is the first cause. Demand is the messenger. Revenue is the final result. The message carried by demand may be positive or negative. A high price often reduces demand, so the rate at which demand changes with price may be negative. Revenue then responds to the changed demand according to its own local sensitivity. Each relationship has its own rate of change. The first relationship tells us how demand reacts when price changes slightly. The second tells us how revenue reacts when demand changes slightly. The chain rule connects these statements. There is an important subtlety in the revenue example. Revenue may depend directly on price as well as indirectly on price through demand. Each sale brings in more money when the price is higher, but a high price may also reduce the number of sales. The total change in revenue therefore has more than one pathway. One pathway goes directly from price to revenue through the amount earned per item. Another goes from price to demand and then from demand to revenue. A complete calculation must account for both. The chain rule handles the indirect pathway, while the ordinary rules for differentiating products or functions of several variables combine the different contributions. For the moment, focused on a pure chain in which the outcome receives the input only through the intermediate quantity. Imagine a set of connected gears. The first gear turns. Its motion turns a second gear. The second turns a third. The final gear does not respond to the first gear by magic or by an independent connection. It responds because motion has been transmitted through the middle gear. The amount of motion passed from the first gear to the second depends on their local coupling. The amount passed from the second to the third depends on another local coupling. The total transfer depends on both. The same idea appears in the chain rule. Each link has a local sensitivity. The sensitivity of the whole chain is found by multiplying the sensitivities of its links. Why multiplication rather than addition? The answer comes from tracking a small change carefully. Suppose the input changes by a very small amount. The intermediate quantity responds. To a first approximation, its change is the input change scaled by the sensitivity of the intermediate quantity to the input. The outcome then responds to the intermediate change. Again, to a first approximation, the outcome change is the intermediate change scaled by the sensitivity of the outcome to the intermediate quantity. The intermediate change already contains the first scaling factor. When the second scaling factor acts upon that intermediate change, the two factors multiply. One conversion is applied after the other. A familiar unit conversion makes this structure concrete. Suppose a speed is described in kilometers per hour and we want the same speed in meters per second. The numerical value must pass through two conversions. Kilometers are converted into meters and hours are converted into seconds. 1 kilometer contains 1,000 meters. 1 hour contains 3,600 seconds. The combined conversion is determined by applying both relationships. The first conversion changes the distance unit. The second changes the time unit. The final factor is not found by adding 1,000 and 3,600. The conversions act sequentially and therefore combine multiplicatively. A small increase in speed measured in kilometers per hour produces a corresponding increase in speed measured in meters per second. The conversion factor tells how much the second numerical description changes for each unit change in the first description. Now imagine a second process that depends on speed measured in meters per second. Perhaps a simplified model assigns a stopping distance according to speed. A change in kilometers per hour first becomes a change in meters per second. That change then becomes a change in stopping distance. The first sensitivity tells how much the middle quantity changes for a small change in the input. The second sensitivity tells how much the outcome changes for a small change in the middle quantity. Every tiny input change must pass through both conversions. That is why the sensitivities multiply. It is worth repeating the structure in words. Begin with a small change in the original input. Multiply by the rate at which the intermediate quantity responds. This gives the induced change in the intermediate quantity. Then multiply by the rate at which the final outcome responds to that intermediate quantity. The result is the induced change in the outcome. This reasoning is local. The sensitivities are evaluated at the relevant current values. If the relationships are nonlinear, the sensitivity may vary from one point to another. The chain rule does not assume that a single constant conversion applies everywhere. Return to the warming rail. At one moment, temperature may be rising rapidly. Later, clouds may slow the heating. The sensitivity of length to temperature may remain nearly constant over a moderate range, while the sensitivity of temperature to time changes throughout the day. The rate of expansion with respect to time therefore changes even if the material law remains stable. The chain rule separates these roles. One part belongs to the environment and describes heating over time. Another belongs to the material and describes thermal expansion. Their product describes the instantaneous expansion rate. This separation is useful because the two links can be studied independently. A meteorological model may estimate the temperature change. A materials model may estimate expansion per unit temperature change. The chain rule assembles them without requiring either model to absorb the entire story. Consider again price, demand, and revenue. If a small price increase causes a substantial decline in demand, then the first sensitivity has a large negative magnitude. If revenue is highly sensitive to the number of units sold, the indirect effect may also be large. Multiplying the sensitivities gives the contribution transmitted through demand. The signs matter. If increasing price decreases demand, the first sensitivity is negative. If increasing demand increases revenue, the second sensitivity is positive. Their product is negative. The indirect effect of price through demand therefore pushes revenue downward. This does not yet determine whether total revenue rises or falls, because price may also influence revenue directly. The chain rule clarifies one causal route, but a full model may contain several routes. In multivariable calculus, the contributions from distinct pathways are added after the sensitivities along each individual pathway have been multiplied. This pathway interpretation is one of the most useful ways to remember the chain rule. Multiply along the path. Add across separate paths. Now consider exercise, heart rate, and oxygen delivery. A person increases the intensity of physical activity. The nervous system and muscles respond. Heart rate changes. Stroke volume may change. Breathing changes. Blood flow changes. Oxygen delivery to tissue changes. No single simple link captures the whole biological system. Yet the chain rule gives a conceptual method for decomposing it. Exercise intensity affects heart rate. Heart rate affects cardiac output. Cardiac output affects blood flow. Blood flow affects oxygen delivery. Each stage has a local sensitivity. Some may be positive, some negative, and some may depend strongly on the current physiological state. The overall response along one pathway is built from the product of the local responses. This does not mean that biology is always represented adequately by a single chain. Feedback loops, delays, saturation, and multiple pathways are common. The point is narrower and more rigorous. Whenever one differentiable quantity depends on another, which depends on another, the derivative of the composite dependence is obtained by combining the local derivatives through the chain rule. Let us pause and reflect. The chain rule does not make the system simple by pretending that intermediate mechanisms do not exist. It makes the system manageable by recognizing them. A complicated story is broken into local links, and the effect is passed through those links in order. This brings us to nested functions. A nested function is a mathematical expression of layer dependency. An outer process receives the output of an inner process. It does not receive the original input directly. Imagine a thermostat system. Time affects room temperature because of weather, insulation, occupants, and previous heater activity. The thermostat responds to room temperature. The heater responds to the thermostat signal. Heater output then influences future temperature. At one instant, focus on the forward dependency from time to temperature to thermostat response, and from thermostat response to heater output. The thermostat does not inspect time itself. It receives a temperature. The heater does not directly inspect room temperature in this simplified chain. It receives a control signal. The inner process takes time and produces temperature. The next process takes temperature and produces a thermostat response. The outer process takes that response and produces heater output. Changing an inner layer changes every layer beyond it, provided the later layers are sensitive to that change. A small change in time alters temperature slightly. That altered temperature changes the thermostat response. The altered response changes heater output. The overall sensitivity is found by multiplying the sensitivity at each stage. The rate of heater output with respect to time combines the rate of temperature change with time, the thermostat sensitivity to temperature, and the heater sensitivity to the thermostat signal. Another way to say this is that the derivative follows the same dependency map as the quantities themselves. The forward calculation moves from input to inner output, then to outer output. The sensitivity calculation passes through the same sequence, multiplying the local rates. When confronting a nested dependency, ask two disciplined questions. What changes first? What quantity receives that change next? These questions prevent a common mistake. One may differentiate only the outermost relationship and forget that its input is changing. The derivative of the outer process describes response per unit change of its own input. To obtain response per unit change of the original input, one must also account for how the inner input changes. Suppose heater output changes sharply when the thermostat signal crosses a narrow range. Then the outer sensitivity may be large. But if room temperature is nearly constant at that moment, the inner rate of change may be small. The total rate may therefore remain moderate. Conversely, temperature may be changing quickly while the thermostat is in a region where its response is almost flat. Again, the total effect may be small. A strong change in one layer does not guarantee a strong overall change. Every link matters. If any one link has zero sensitivity at the current point, the product along that pathway is zero. A local change may reach that layer and then fail to influence what comes afterward, at least to first order. This phrase, to first order, is important. Derivatives describe the leading response to sufficiently small changes. If a derivative is zero, higher order effects may still exist. The chain rule concerns the first order transmission of change. The same logic extends beyond a single intermediate quantity. A process may contain 10 layers or 100. In modern computational systems, nested transformations are common. One stage normalizes data. Another applies a nonlinear response. Another aggregates information. Another produces a final output. For a long chain, the overall sensitivity is a product of all local sensitivities along the route. This can produce very small overall effects when many factors have magnitudes below 1. It can produce very large effects when many factors exceed 1. These phenomena appear in numerical analysis, dynamical systems, control theory, and the training of layered statistical models. The essential calculus remains the same. Follow the dependency order. At each layer, identify the response of the next quantity to the present one. Multiply those local responses. The chain rule also appears in related rates problems, where several quantities change with time while remaining connected by a geometric or physical relationship. Imagine a spherical balloon being inflated. Its radius changes with time. Its volume changes because volume is geometrically determined by radius. Time does not appear in the geometric relationship between radius and volume. Nevertheless, both radius and volume vary with time. The rate of volume change depends on two things. It depends on how sensitive volume is to a change in radius at the balloon's current size. It also depends on how quickly the radius is changing with time. A large balloon gains more volume from the same small increase in radius than a small balloon does. This is because the geometric sensitivity of volume to radius increases as the balloon becomes larger. If two balloons have the same rate of radial expansion, the larger one generally has a greater rate of volume increase. The chain rule combines the geometric sensitivity with the temporal rate. One link runs from time to radius. The next runs from radius to volume. Notice that the geometric relationship may be known even when radius has not been explicitly described as a function of time. Perhaps an experiment tells us only the instantaneous rate at which the radius is increasing. That is enough to determine the instantaneous rate of volume change, provided the current radius is known. This illustrates a broader principle. Relationships need not always be solved explicitly before their rates can be connected. An equation may constrain several quantities without isolating one of them as a direct function of another. Differentiating the relationship with respect to time reveals how the rates must be related. This method is often called implicit differentiation. The chain rule is its engine. Whenever a changing quantity appears inside another operation, differentiating with respect to time requires us to multiply by the rate at which that inner quantity changes. Consider a point moving along a circle. Its horizontal and vertical positions change with time, but they are constrained by the fixed radius of the circle. Even without solving explicitly for vertical position in terms of horizontal position, the geometric constraint forces a relationship between the horizontal and vertical velocities. The unsolved relationship still restricts how the quantities may change. They cannot vary independently. The chain rule translates the static constraint into a relation among instantaneous rates. The same idea applies to expanding surfaces, moving shallows, filling tanks, cooling objects, and changing concentration. A quantity changes indirectly through another changing quantity. The direction of dependency must be identified carefully. In the balloon example, time changes radius, and radius determines volume. It would be misleading to say that volume independently causes the radius in the chosen model. The geometry permits either quantity to determine the other under suitable conditions, but the physical process tells us which rate is supplied and which rate is inferred. Dependency direction is therefore partly a matter of mathematical representation and partly a matter of the model mechanism. The chain rule follows the direction used in the model. Let us pause and summarize. There is an original input. That input changes an intermediate quantity. The intermediate quantity changes a final outcome. Each link contributes a local rate or sensitivity. The total first-order effect along the chain is obtained by multiplying those sensitivities. This principle becomes especially clear through small changes. The input changes slightly. The intermediate quantity changes by approximately its local sensitivity times that input change. The outcome changes by approximately its unlocal sensitivity times the intermediate change. Substitution places one scaling inside the other, producing multiplication. The exact derivative statement emerges by taking the limit as the input change approaches zero. The approximation error becomes negligible compared with the input change under the usual differentiability assumptions. Thus the chain rule is not merely a mnemonic based on cancelling units. It is a theorem about the derivative of a composite function. The unit language remains helpful. The first rate may be measured in degrees of temperature per minute. The second may be measured in millimeters of expansion per degree. Multiplying produces millimeters per minute. The intermediate temperature unit disappears from the final description because it serves as a connecting quantity. This apparent cancellation reflects the logical composition of rates. It is useful for checking whether a calculation is dimensionally sensible. But units alone do not prove the chain rule. The proof rests on the local linear behavior guaranteed by differentiability. Differentiability means that near a point, a function is well approximated by a linear response. For a one-dimensional input, a small input change produces a function change equal to the derivative times the input change, plus an AR that is smaller than the input change in the limiting sense. If an inner function and an outer function are both differentiable, the inner change is locally linear in the original input change. The outer change is locally linear in the inner change. Substituting the first local approximation into the second yields a product of derivatives, while the combined error remains negligible at first order. That is the rigorous foundation. Local linear approximations compose, and their scaling factors multiply. This interpretation extends naturally to functions of several variables. In higher dimensions, a derivative is not merely a number. It is a linear transformation that sends a small input displacement to the corresponding first-order output displacement. When one differentiable transformation is followed by another, the derivative of the composite transformation is the composition of the two linear transformations. In coordinates, this becomes matrix multiplication. The order matters because the output of the first linear map becomes the input of the second. The familiar one-dimensional chain rule is the special case in which the linear transformations are simply multiplication by numbers. Composing those transformations means multiplying the numbers. This higher dimensional perspective shows that the chain rule is not an isolated computational trick. It expresses a general structural fact. The best linear approximation to a sequence of processes is obtained by composing the best linear approximations to the individual processes. The dependency map may branch. One input can affect several intermediate quantities, and those quantities may jointly affect the output. In that case, each pathway contributes its own product of local sensitivities, and the contributions are combined according to the linear structure of the derivative. Return once more to revenue. Price affects revenue directly through money earned per item. Price also affects demand, which then affects revenue. The total derivative includes both routes. The direct route contributes its own sensitivity. The indirect route contributes a product of sensitivities. The effects are added because small changes from distinct first-order routes combine linearly. This viewpoint is useful in economics, physics, engineering, statistics, and biological modeling. It is also useful in pure mathematics whenever objects are built by composing maps. A change of coordinates is a composition of transformations. A parameter enters a polynomial whose roots may influence another construction. A matrix depends on parameters, and its determinant depends on the matrix entry. A probability distribution depends on parameters, and an expected value depends on the distribution. In each case, change passes through layers. Even when the final application looks complicated, the chain rule asks for the same discipline analysis. Identify the intermediate objects. Determine which quantity depends on which. Compute or characterize the local derivative of each link. Compose the derivatives in the correct order. It is worth repeating that order cannot be ignored. If one process takes temperature as input and produces expansion, while another takes time as input and produces temperature, the temperature-producing process must act first. The derivative composition follows that order. In one dimension, ordinary multiplication hides this issue because numbers commute. In higher dimensions, matrices generally do not commute. The derivative of the outer transformation acts after the derivative of the inner transformation. Reversing them may be meaningless or incorrect. The chain rule therefore records both magnitude and architecture. It tells us how strong the local responses are and how the dependency network is organized. There is also a useful relation to inverse processes. Suppose one quantity changes with another, and the relationship can be inverted locally. If the forward sensitivity is non-zero, the sensitivity of the local inverse is its reciprocal in the one-dimensional setting. This follows because moving forward and then backward produces no net change beyond the original input. The composite process is locally the identity. The chain rule says that the product of the forward and backward sensitivities must equal the sensitivity of the identity process. In higher dimensions, the analogous statement uses inverse linear transformations. This idea lies behind the inverse function theorem, where a non-singular derivative permits a differentiable map to be inverted locally. Once again, the chain rule reveals structure. It connects local behavior of a function with local behavior of its inverse. It also supports the implicit function theorem, where a constraint can locally determine some variables in terms of others. The expanding balloon is an elementary related rates example, but the same principle scales to sophisticated systems. Constraints define allowable states. Motion remains within those constraints. Differentiation translates the constraint into a condition on velocity. In mechanics, a moving body may be restricted to a surface. In optimization, feasible points may satisfy equations. In differential geometry, coordinate descriptions overlap through transition maps. The chain rule ensures that derivatives transform consistently when one description is replaced by another. This consistency is one reason derivatives have intrinsic meaning. Although numerical coordinates may change, the composition laws governing derivatives remain stable. The chain rule tells us how local linear descriptions fit together. Let us now return to the simplest verbal form. Input, intermediate effect, final effect. The input changes first. The intermediate quantity receives that change. The outcome receives the resulting intermediate change. Each link has a local sensitivity. The overall sensitivity along the chain combines every local sensitivity in sequence. In one dimension, the combination is multiplication. For linear maps in several dimensions, it is composition, represented by matrix multiplication after coordinates are chosen. If the chain contains more layers, continue in the same manner. Time changes temperature. Temperature changes resistance. Resistance changes current. Current changes power. Power changes temperature again. A feedback system may form a loop rather than a simple chain, but every local passage of change still uses the chain rule. Loops require additional analysis because later effects return to influence earlier quantities. Differential equations often describe such evolving feedback. Yet the local derivative calculations inside those equations still follow the same principle. The chain rule is therefore both elementary and foundational. It begins with simple rates and extends to differential equations, geometry, optimization, probability, numerical computation, and many layered models. There is a broad structural lesson here that reaches beyond calculus. Mathematics often becomes manageable when a complicated object is decomposed into simpler stages and the rules for recombining those stages are understood. Abstract algebra follows a similar intellectual pattern, although its objects and operations differ. A field extension may be studied through a tower of intermediate fields. A module may be understood through submodules, quotients, and decompositions. A polynomial may be studied through its factors and through the fields containing its roots. Symmetry provides another organizing layer. The symmetries of polynomial roots form groups, and those groups record which algebraic relationships remain unchanged when the roots are permuted in allowable ways. Galois theory connects the structure of field extensions with the structure of symmetry groups. Questions of solvability can then be approached by passing through intermediate structures. One does not treat a polynomial equation as an opaque whole. One examines its roots, the field they generate, the symmetries preserving algebraic relations, and the decomposition properties of the resulting group. The details are different from differentiation. Algebraic structures do not carry rates of change merely because they are arranged in layers. Yet the shared habit of thought is important. Identify the relevant objects. Determine how one layer acts on or constrains the next. Preserve the information that remains invariant. Reconstruct the global structure from local or intermediate pieces. In calculus, the invariant organizing principle is the composition of local linear approximations. In abstract algebra, one often studies homomorphisms, kernels, images, quotient objects, fixed fields, and symmetry groups. These tools identify what survives transformation and what information is lost. A field homomorphism preserves addition and multiplication. A module homomorphism preserves the module operations. A group action preserves the structural rules of the group while moving elements of another object. Factorization exposes how a polynomial is assembled from simpler polynomial pieces. Decomposition is valuable only when the pieces can be recombined coherently. The chain rule gives such a recombination law for derivatives. Algebraic theorems give corresponding laws for extensions, modules, factors, and symmetries. Let us pause and reflect one final time. A long dependency becomes intelligible when its intermediate stages are named. A small change becomes intelligible when each local sensitivity is identified. A composite process becomes intelligible when the order of its layers is respected. The same common discipline serves throughout mathematics. For fields, study intermediate extensions and the maps that preserve operations. For modules, study submodules, quotient modules, and decompositions. For polynomials, study factors, roots, and the fields in which those roots live. For symmetry, study transformations that alter appearance while preserving structure. For solvability, determine whether the global problem can be reduced to a sequence of compatible intermediate steps. The chain rule expresses this discipline in the language of change. The original input produces an intermediate effect. The intermediate effect produces a final effect. Each link contributes a local rate. Along one pathway, the rates combine in sequence. Across distinct pathways, their contributions combine according to the derivative's linear structure. When a system seems complicated, do not force a direct leap from the beginning to the end. Locate the messenger quantities. Determine what changes first. Determine what receives that change next. Examine each local relationship at the current state. Then combine the links in their proper order. Calculus follows change by identifying how influence is transmitted. Abstract algebra studies structure by identifying what remains unchanged under allowable operations and transformations. Both subjects become clearer when the layers are exposed, the connecting maps are understood, and the whole is reconstructed from its parts. Begin with the input. Observe the intermediate effect. Continue to the final effect. Respect every dependency, every local sensitivity, and every structural connection. Follow calls through every layer.